Hello, welcome to one of the plenaries for the CosmoConv online practice conference. I have with me José Luis Bernal. This is your talk, so do you want to maybe introduce yourself quickly?
Hi, yeah, sure, thank you. I'm José Luis Bernal. I've been working a lot on like the Hubble constant tension and also like scale structure and intensity mapping. And today I'm going to talk about like one of my last works, checking the robustness of the standard Baryon acoustic oscillations constraints for models beyond ΛCDM and why this is important for the Hubble constant tension.
And you're a postdoc at Johns Hopkins University.
Yeah, that's right.
So you kind of already covered this a little bit, but if you want to go into a tiny bit more detail and a short summary of what you're going to be talking about, do you want to have a sort of 2-minute description of?
Sure. So, well, we all know there's this tension with the Hubble constant between different experiments, mostly between low redshift and high redshift experiments, and the constraints from galaxy surveys, especially regarding the Baryon acoustic oscillations and the standard ruler, are key, as I will explain later, in order to do these constraints and constrain especially low redshift expansion history, but also give the connection between these low redshift and high redshift observables. So given their importance and how these proposals to change and to solve the Hubble constant tension, there was a common worry, especially from the theoretical community, that since the standard BAO analysis assumes a fiducial cosmology for getting the results, especially one using ΛCDM, whether these results were valid to use and to constrain models beyond this cosmology. So this is what we wanted to check, because we even saw some works in which BAO constraints weren't used. BAO measurements weren't used to constrain, and is like such an important data set that can't be left out of the analysis. Later, if time permits, I will talk about like how BAO at higher redshift from line intensity mapping can help for constraining models that may solve the Hubble constant tension.
Cool. On that first point, it's definitely something every time someone's given a talk using a data set that was calibrated on ΛCDM to constrain beyond ΛCDM, you can almost guarantee it's going to be one of the questions from the audience of like, how can you trust this? So I think this is a very, very important thing to really think about and make sure people are getting right. So if the people at the conference only took 2 things away from the conference about your work, what would you like those 2 things to be?
Okay, so I think like there are 2 key things. One of those is like, as I will show, so far, and at least for the models that we check, but in the paper we provide arguments for other models, is that compressed BAO measurements on the compensatory parameters and the scaling parameters are valid to constrain model beyond ΛCDM, so the standard data products can be used.
Okay.
And also I wanted to, this makes that the fact that some solutions of the Hubble constant tension that only rely on a phase shift of the acoustic features in the CMB are not valid and are very constrained by the data, as I will show later.
Cool.
Also, like the second key point is that the line intensity mapping Baryon acoustic oscillations, since line intensity mapping is one of the few ways to reach such a high redshift beyond like redshift 3 or so, will be key in order to extend the cosmic distance ladder towards those high redshifts, and will be key to constrain post-recombination solutions of the Hubble constant tension.
Cool. So you've gone into this a little bit with your 2 simple things you want people to take away, but if you want to go further into the background of why you've done this particular research, and if you want to bring up the slides as well, that might be a good time.
Okay, yeah, I think I will share the screen.
Cool.
Let me. Okay, so is it out there?
Yep.
Okay, so well, these are the the two papers I'm going to talk about, I'm going to give like more weight to this one about like the robustness of BAO, as I said. And here is mostly the current landscape, although this changes almost every week, of the current constraints on the Hubble constant tension. And I'm showing in blue the measurement by Planck 2018, assuming ΛCDM. In black, and showing results from the local universe. And these results are model independent because you don't need to assume any cosmological model in order to obtain these values of each node. In green, I'm showing results that need to assume a cosmological model because depend on quantities that are farther away, or that you need to assume this model but don't depend on the early universe. And finally, in magenta, I'm showing results that rely on the early universe. And as you can see, there's a clustering of results at higher Hubble constant values for local measurements with respect to those, especially from the Planck and BAO using early Big Bang nucleosynthesis to constrain H0, that these are clustered towards low redshift. So this seems to confirm that there's a high redshift versus low redshift tension. And since like some years ago, this is not anymore only the results from SUS collaboration with respect to Planck, assuming ΛCDM, but like they have like a lot of confirmation from other results and collaborations. And there's a complete suite of possible solutions, both modifying late times physics or pre-recombination physics.
I can't help but ask a question about what the green one that just says clocks is. I haven't heard of that before.
This is like, it's called cosmic clocks, this one. Yeah. This is using the fact that quiescent galaxies are very similar, and you can assume that, so I'm not an expert about this, so okay, no, yeah. This is like a very blurry description, but you can assume that the formation time of these galaxies are approximately the same, and having like, you can relate the redshift of the emission of those galaxies with the age of this, so that you can measure directly the Hubble parameter.
Cool.
So at low redshift, the most important quantities that we have in order to constrain the expansion history are the BAO and supernovae, which provide complementary standard ruler and standard candles, respectively. And I say that they are complementary because while BAO provide a normalized constraint from the expansion history with the normalization in terms of the product of the sun horizon at radiation drag times the Hubble constant, the sampling in redshift is still too sparse so that we can't constrain the shape of this expansion history. On the other hand, supernovae, the sampling in redshift is very abundant, so we can constrain very well the shape, but since we don't know the intrinsic luminosity of the supernovae, we don't know the normalization of this measurement of the expansion history. Therefore, once you combine the two of them, you can build a consistent and normalized cosmic distance ladder. And this is what you can do, for example, using the Hubble constant tension to calibrate supernovae and then combine them with the Baryon acoustic oscillations. This is called the direct distance ladder. But you can also use high redshift quantities, as for example the CMB, to calibrate the BAO, combine them with the supernovae in order to normalize it, and finally give obtain a measurement of the Hubble constant. And this is the inverse distance ladder. Of course, these two procedures need to match. So no matter which of the two anchors of the cosmic distance ladder, which would be RS or H0, you use, they need to coincide the two distance ladder.
Yeah.
And if you vary, like if you free these anchors, you can constrain directly the product, which is what we have called in some works the low redshift standard ruler. So doing this and parameterizing basically the expansion history with cubic splines so that we don't assume any specific cosmological model and give complete freedom to expansion history.
I guess you assume that it's smooth, but that's probably a reasonably valid assumption.
Yeah.
So there hasn't been a sudden jerk or anything in the expansion that can't be fitted by a cubic spline. But
yeah. So we assume that it's smooth. We assume that the general relativity holds. Sorry, that the gravity follows a metric theory.
Mm-hmm.
It's not even needed to be like GR. And that the BAO and supernovae can be used as a standard ruler and standard candles.
Mm-hmm.
And for these results, we also assume that the universe is flat. But there are also some results in these papers, in Verde et al. In 2017 especially, in which we free this assumption and also vary the curvature of the universe. So here I'm showing all independent results, both experimentally and theoretically. I'm showing in orange the constraint, the marginalized constraints of the sun horizon at radiation drag from Plan 2015, doing from an analysis that only assumes pre-recombination physics, sorry. So it's completely dependent on what happens at the late times. Mm-hmm. As I said, the measurement from SUS is independent from any cosmological model. Mm-hmm. And this magenta line band is the constraint that we obtain of the product of the sun horizon at radiation drag times is not, using these cubic splines for the expansion history at low redshift, and varying also at the same time the two anchors. And we found that this is very well constrained. So this product is constrained to the 2% precision, even in a completely, so even without assuming any specific cosmological model. And also that the expansion of the history of the universe is very constrained to be like ΛCDM. So this seems that there's no possibility to solve the Hubble constant tension changing the expansion history at very low redshift. Hmm. Here in blue, I'm showing the results of combining our magenta results with SUS, and this is what will happen if we will combine it with the sun horizon at radiation drag. And as you can see, there's like this clear mismatch. And we need the sun horizon from the measure from the CMB to be smaller to match a higher value of the Hubble constant. So this is a very clear way to frame this tension that is in reality a mismatch between the two anchors of the cosmic distance line. Mm. So this is why BAO is so important to constrain and to solve the Hubble constant tension, because it connects the two sets of experimental observables that are in tension, that are low redshift and high redshift universe.
So isn't it also true that you can make an even stronger claim that, because you've used this yellow line for RS from Planck, but if you just use it from BBN, so you don't even have to refer to Planck, do you not still get like the green contour in more or less the same spot? Isn't it even visible on your previous slide?
Yeah, so if I would hear the green contour, like since this sun horizon would be a bit wider, there would be a higher, like a larger contour here. However, that would be the case. We can obtain the BBN measurements from omega Baryon, but we would need still some kind of prior on omega cold dark matter in order to measure the sun horizon.
Okay. Did you not have this result on the previous slide? Like it was one of the measurements?
But here.
Oh, sorry.
The BAO. Yeah. And we wanted to make the claim that all of the results were completely independent in the other plot.
All right.
So here we are using the BAO to constrain models that are, especially at low redshift, completely independent. And as I was saying before, a standard analysis of BAO assume a fiducial model of LCDM and then claim that you can use the compressed results for any model, that they are model independent. So this is what we wanted to check, and this is the main motivation of this for this work, basically.
Cool. So yeah, let's get into it. What is it? How did you check this, and how do you know? How can you be confident that it works?
Okay, cool. So first of all, I'm going to discuss what is the actual cosmological information that is in the BAO measurements, because this will help to understand why this may or not be model independent and robust for constraining beyond =LCDM cosmology. So we know that the BAO feature after a combination is frozen in the matter over densities, and this is why we can use it as a standard ruler, because we know its physical scale. However, large-scale structural observations, as it could be like from a galaxy survey, they measure the galaxies as function of redshift and positions on the sky. But we use later, in order to fit our models, three-dimensional summary statistics of the clustering, as it can be the correlation function of the power spectrum. And to do this, to measure those summary statistics, we need distances. And here is the first step where a fiducial cosmology is needed. We need to transform these redshifts into distances, assuming a cosmology. And if this cosmology is not the true cosmology that we are observing on the universe, we will add artificial distortions to this clustering, and our measured power spectrum, for example, would be distorted. Yeah. And these distortions are added to the standard physical distortions that come from redshift space distortions. Yeah. So what we could think, here I'm going to focus only on the BAO scale in 2D, but this is extended that it applies to all scales, and of course in 3 dimensions. So when we transform redshifts into distances, and angular separations into distances, this is basically what we have. The perpendicular to the line of sight distance would be the angular diameter distance times the angular separation, and the parallel distance would be depending here on the Hubble parameter. So in reality, we expect the BAO scale to be completely isotropic. So this could be a sphere of our assumed fiducial sonorization at radiation drag. But since we are introducing these distortions, the line of sight direction and the perpendicular direction will be distorted in principle different ways, because this has like different cosmological dependence, the angular diameter distance and the Hubble parameter. So therefore, this will be distorted. Now, a standard cosmological analysis of the BAO, what they do is they assume a fiducial template and they distort it in order to try to fit these distortions due to the assumption of the ground cosmology. So if we assume a template, in that case, this scale is again changed, even if we have assumed a perfect cosmology during the analysis, because in our fixed template can have a different horizon from the reality. So we need also to take into account that horizon can be different, so we need to rescale too. But this distortion would be isotropic. For the two quantities.
This might be obvious to everyone, but just in case it isn't, you're also talking about this statistically, right? Because if you look at any region of the sky, then nonlinear clustering would make any of these perfect circles just a little bit distorted in one reason or another, just because it statistically happens to be a bit ellipsoidal. But the idea is that once you look over the whole statistically large sample, you should get an average that goes back to a sphere.
Yeah. Even without nonlinear collapse, like there would be, even in the perfect real space clustering, there will be like wiggles here, just because there are like fluctuations. It's true that nonlinear clustering and nonlinear collapse makes those deviations from this perfect sphere worse, but you can use techniques as density field reconstruction in order to make it more closer to the linear prediction, and the BAO feature being more significant. So as I was saying, what the standard cosmological analysis do is assume a template from a fiducial cosmology. In there, isolate the BAO feature, and then distort this template such that you manage to fit that specifically distortion that you observe on the data and have introduced due to the assumption of a wrong cosmology in order to transform redshift into distances. So basically what you are measuring from the BAO in reality, from the Alko-Paczynski effect, is this this distortion that you've created because you haven't matched the real cosmology when transforming redshift into distances. Yeah. And you can fit this and model this with rescaling parameters that could be alpha parallel and alpha perpendicular. And there are, as I was saying, two contributions. One from the Alko-Paczynski effect, which I marked here in green, and one by the fact that you have assumed a fiducial sonorization that might not be the true. So you need to rescale your BAO scale in your template. And from here, you can, since the angular diameter distance goes as 1 over h naught, you can see clearly that the normalization of these rescaling parameters goes as the product of the sonorization at radiation drag times h naught. And this is why I was saying before that you can constrain very well this from the BAO. Okay. However, here you are assuming a fit template and only distorting it a bit. And if you have assumed, for example, for your template a wrong spectral index for the tilt of the power spectrum, you will never fit perfectly your observed clustering. And this is why you need to also marginalize over the broadband of the clustering in order to account that you may have some other differences in your template with respect to reality, but this is not related to the BAO scale. So you marginalize over them. Okay. And what we want to check if this marginalization here covers all the possible cases for models beyond ΛCDM. Because it had been shown before that for expansion history at low redshift beyond ΛCDM, this parameterization was very, very accurate. But if you modify the BAO feature in the early universe, you may have some effects on the BAO feature with respect to your template that are not only covered by a rescaling of the sono horizon.
Yeah, okay.
I can show here quickly some plots. I don't want to get into this because it will take a lot of time, but here we are showing only the BAO feature and its ratio with respect to the ΛCDM, but in only a single parameter. And since, for example, here, the sono horizon at radiation drag changed a lot, changing omega baryon, what I'm doing is rescaling the sono horizon at radiation drag directly in this plot, so that everything that is shown here is what is left outside the standard BAO analysis. If this deviates a lot from having especially these zero crossings always at the same point, it could mean that there's a potential bias on our measurements.
I see. And
for models beyond ΛCDM, this can be the case.
Okay. I guess if people want to know more about this, then that's the whole point of having the discussion parts of the conference. They can sit down with you and go into detail on this for however long they want.
Yeah. I will be glad, but it's very specific things, and there's a clear discussion about this in the paper too. So I'm glad to talk about that.
Cool.
And this is basically the money plot of the paper. So what we did was fixing a fiducial template. So we will always use the same fiducial ΛCDM model to analyze the power spectrum. We generated a synthetic power spectrum following different cosmological models. Concretely, and each cosmological model corresponds to a row here. We checked ΛCDM, ΛCDM plus an effective. An effective is known to introduce an extra phase shift of the Baryon acoustic oscillation. So we would expect this to introduce a feature in the BAO that is not modeled by the rescaling of the sono horizon. So we would expect this at some point to be biased if there's a problem. And we consider two other models that have been proposed to solve the Hopkins tension. One of them is the early dark energy model, which proposes an scalar field that becomes the dynamical Fourier combination and introduces basically a boost on the expansion history around the matter radiation equality. And this other one is the dark matter neutrino interactions, which introduces an interaction between neutrinos and a fraction of the dark matter, such as the free streaming of neutrinos is somewhat inhibited. And this wouldn't change the sonorization at radiation drag, but will change only the phase shift, will reduce the phase shift of the acoustic oscillations on the BAO, such as you would measure the peak at lower, corresponding to a lower L, without changing the sonorization. And in order to recover that, you will need a higher H0. I have an expression later for that.
Just can I clarify something? When you say plus ineffective, you don't mean that ineffective is 1, you mean that you've added 1 to ineffective, so it's more like 4.
I added ineffective as a, ineffective 1 and ineffective 2. It's not that I added 1 or 2. Like these numbers 1 and 2 corresponds to good fits to Planck power spectra and bad fits. Number 1, that is shown in blue for all plots, corresponds to the best fit of Planck power spectra. While for the bad fits, what we do, and we saw it in red and correspond to the number 2 cosmologies in the in the legends, what we did is we fixed one of the cosmological parameters to a value 3 sigma away from the best fit from Planck. And change accordingly the rest of the cosmological parameters so that this fit will correspond to at least 3 sigma away from what we observe from Planck. And each column corresponds to different surveys. Here is both LOC and CMAS that have already finished. And here are 2 forecasts for DESI for redshift beams of 0.2 of width and center of 0.8 and 1. And I'm showing with a circle the best fit of our analysis, and from a star, the real value that we know that this will have. So alpha parallel and alpha perpendicular, as a reminder, are here. And since they are compared always to the fiducial template, they won't be 1 and they will change from model. This is why each of these blobs is centered in different positions.
But if the star and circle still lie on top of each other, then they're measuring the correct value, which is the incorrect value you put in, but it's the correct value for the data.
Yes, that's right. And as you can see, like for most cases, the fit is astonishingly well. The only problem would be the DNI models, but for the models that are a good fit to Planck, which is in blue, all biases are below 0.3 sigma. And only for very bad fits, again, I remember 3 sigma away from Planck, and only for this case, then this is our largest bias, and is around 1 sigma. It's 1.04 sigma, if I don't remember wrong. So even for like extreme scenarios, it seems that BAO analysis, standard analysis are very robust towards cosmologies beyond ΛCDM, even if they assume a template from ΛCDM.
Cool.
In the paper, and I'm happy to extend it in the discussion about this talk later, we provide also a way to redo this analysis for your preferred cosmology. And in the case there's a clear bias, we provide some guidance in order to amend it and perform the analysis in a different way so that that bias can be removed.
Cool.
Okay, so as I was saying, this is the case for comparing DNI cosmologies, and the authors of DNI, since they were worried about the possible bias in the in the BAO, they didn't include these models, this data in the fit. And this is what I was saying before. So this is the phase shift, this 5, and the number peak of the CMB would be located at this position. So P times pi minus the phase shift and the projection of the sun horizon of the acoustic feature. This is why if you reduce the phase shift due to the inhibition of the free streaming of the neutrinos, you would move you would displace the peaks towards larger multiples, but without changing the sun horizon. So in order to recover the observation from Planck, you need to increase the Hubble constant. And this is the main logic behind the motivation of this model to solve the Hubble constant.
Okay.
However, if we compare with existing data, so here I'm showing the angular diameter distance and the Hubble parameter, and comparing it with existing data in black dots, we can see that while the ΛCDM fiducial cosmology provides a very good fit to these observations, the DNI best fit reported in that paper that is Ghosh et al. 2019, I think. It provides a very bad fit. And for the low redshift galaxy BAO, which is the standard dataset that is included in Planck analysis, for example, the delta chi square, again, having 2 more parameters, is 6. And this delta chi square is worse for DNI. So this seems to support the idea that you can't rely only on a phase shift in order to solve the Hubble constant tension, because basically you will be changing H0, but without changing the sun horizon. And we have seen before that the product of the sun horizon and the H0 is very well constrained by the observations. Okay. So this is a clear, very powerful statement that may guide theories in order to develop their models trying to solve the Hubble constant.
Cool.
Okay, so we're
recording again.
Okay, so well, I talked before about like how important BAO measurements are for cosmology in general, but in particular to solve the Hubble constant tension. The problem is that if we compare what we know or think is the evolution of the universe since recombination to today, there are all these huge volumes and redshift range that we haven't proved directly. There are some constraints coming from the CMB lensing, but these are peaked, the kernel from CMB lensing are peaked around redshift 2. So we haven't any observational constraint from all these redshift from around redshift 2.4, which is the highest redshift measurement from the Lyman Alpha Forest BAO, until redshift 1000. And here we assume that the expansion history of the universe is completely determined by omega matter, because that's the prediction of ΛCDM and most models, but we don't know, like we lack that observational evidence. And one could say, okay, but maybe with DESI or Euclid or LSST, you can go farther in redshift. You can go farther in redshift and probe this range. The problem is that galaxy surveys rely on very significant detections of galaxies so that they can detect it and count it as a single point. And they count their points. So they throw away a lot of information. And at high redshift, let's say redshift beyond 5, which I think is the most optimistic proposal for galaxy surveys, galaxies would be too faint and too sparse in order to be used for cosmological analysis. However, line intensity mapping, which proposes to use all integrated emission from atomic or molecular lines, using all the radiation coming from galaxies and the intergalactic medium along the line of sight, could provide, at these redshifts in which you can't reach otherwise, will provide a 3-dimensional map with all the information coming from the incoming photons. So you could do tomography up to very, very high redshift. And since the emission of this line is triggered by, so it depends on the abundance of the gas, and that could be related with the matter over densities. This is a biased tracer of the density fluctuations, and it contains cosmological information. Therefore, it will help us to probe cosmology on this redshift range. The problem is that the processes that trigger this, the emission of these lines or the absorption of these lines in some cases is very complicated, and it contains a lot of astrophysical uncertainties right now. And we need to clip this signal because the cosmological information is degenerate with the astrophysical information here. I won't go into that right now. I have a paper that appeared last year proposing a model in order to disentangle the astrophysics and cosmological information from the clustering and specifically the power spectrum from line intensity mapping. But using that modeling, you could measure.
Well, if people want to know more about the modeling, then again they can track you down during a conference and ask for those details.
So using that model, we can measure the BAO, and what we did last year was forecast the potential of different planned and future surveys for line intensity mapping on the angular diameter distance and the Hubble parameter. Here we are focusing on star formation related line intensity mapping, in star formation related lines, which are not normally the most famous one, because when most people hear about intensity mapping, they would directly think of the 21 centimeters lines. But here we wanted to focus on these lines because it is expected that the foregrounds for these lines are much well under control, so that it will be a cleaner measurement in principle. So here I'm showing forecast for COMAP, which is an ongoing experiment targeting the CO line, for spherics, which will fly in 2023 and will include a line intensity mapping survey targeting H alpha and Lyman alpha lines. They will also target other lines, but they will be too faint to use them for cosmology. And also, being a bit more futuristic, we consider a C2 stage 2 experiment that could be an upgrade of the ongoing concerto, and an experiment in which what we envision to be the stage 3 of intensity mapping target is CO, which is thought as an upgrade of COMAP. And as you can see,
C2 is measuring what element or compound?
The C2 line.
Oh, okay. So carbon.
Yeah.
Yeah. Okay. I guess that's obvious. I thought it was the second of Anyway, I might edit what I'm saying right now out, but I thought the stage 2 and C2 were the same two.
Oh yeah. Sorry.
No, it's fine.
So here we compare it in purple with current measurements, and in orange with the forecast of DESI. And here you can see that COMAP2 and spherics will be competitive with the Lyman alpha forest BAO from DESI, and are also around the same redshift range. But with spherics and future other experiments, we will be able to expand our constraints of the expansion history of the universe up to much higher redshifts than you can do with galaxy surveys. And I just wanted to emphasize that here for the Hubble parameter, the constraints from spherics look much worse than for the angular diameter distance. But this is because the spectral resolution of spherics, which will be much worse than their angular resolution, which will be very, very good. And this is why we can measure much better the BAO on the transverse direction than on the line of sight direction.
This IMS3 one looks like it does well in both.
Yeah. IMS3 and COMAC, for example, is pretty similar, both resolutions. The same for the C2 stage 2, and the stage 3 is very futuristic, but will provide very well very good constraints for the expansion history. And what this is important is because if we do the same game as before and try to constrain the expansion history of the universe with splines and without assuming any cosmological model, this is the difference what we have comparing current data with the data that I include before for intensity mapping. Beyond redshift 2.4, we won't have any constraints. So if we don't assume any cosmological model, there can be whatever there.
Right.
And however, with our forecast for intensity mapping, we will be able to probe the expansion history of the universe with like around the level of 2-5% until redshift 7-8, which will provide a perfect reach in order to link low redshift and high redshift observations. You can add then later to the velocity-induced acoustic oscillations constraints that are expected to be obtained by HIRA, and this is a work by Julián Muñoz that you can check. I think it's last year, and we'll provide also very good constraints around redshift 15 or 20, so that you can link and probe very well the expansion history up to redshift 20, and beyond redshift 20, there's now not enough time in order to accommodate all the change in the expansion history needed to solve the Hubble constant tension. So intensity mapping will provide a perfect way to probe post-recombination solutions of the Hubble constant tension. And this is why this was the motivation of all this work, proposing and advocating for the use of intensity mapping in baryon acoustic oscillations.
This is something that's going to take a decade or so to actually get the data for, or?
Well, it depends. Like for this very well constrained, it will require a lot of time, probably more than a decade, because we are assuming futuristic experiments. But if you see here, the angular diameter distance for spherics, which will fly, as I said, in 2023, and I think it's like maybe a 3-year survey. I don't know. It's a 3 or 5 year survey. So by the mid-2020s, we will have, or we expect to have, good measurements of the BAO at redshifts that have been probed so far.
Okay, cool, awesome.
So right now there's a very interesting and active landscape of the experimental advancement for line intensity mapping missions. So I'm optimistic about this.
Yeah, it's exciting.
So yeah, I think that's most from my side.
Cool. So we've got maybe 1 or 2 minutes left if you want to just, I guess on the observational side, where to next is wait for these experiments and things. And if on the theory side from your first half, I guess people can be a bit more bold about doing beyond-LCDM. But do you have anything else you'd want to add about where you think things are going next? What are you going to be working on next?
So I'm very excited about like all the possibilities and opportunities that line intensity mapping observation provide, not only related with BAO, but with other features in the clustering, or even for astrophysics. It will be a perfect probe for ionization. So I'm pretty excited about all that. It's a new window for all of us to work on that. And regarding the Hubble constant tension, I think that in my opinion, the best way to address it is being as agnostic as possible and do model-independent analysis so that we can understand the nature of the tension and motivate the model building so that new theories are probed. Yeah. And of course, as with the line intensity mapping BAO, look for new observables or probes to constrain these and disentangle these theories.
Cool. Well, that's almost exactly 45 minutes. I think it's like 43 minutes at the moment.
Cool.
I wrote down a heck of a lot of questions while you were talking, so hopefully everyone else will have lots of questions as well. The discussion will just be dominated by me asking you questions. So thanks. And yeah, like everyone, write down your questions, and look forward to discussing this in later in the week from when people will be actually seeing this video. Thanks.
Okay. Yeah, looking forward to it.